In addition to his research, he teaches nuclear chemical engineering and fuel cycle classes. Before here, he's also been a corporate fellow at Oak Ridge National Laboratory, and he is a fellow of the American Association for the Advancement of Science and the American Nuclear Society. So we're up for a great talk. Thank you.
Thank you. Well, I'll just use the mic I've got on me.
Oh, you have a mic?
Yes, I have a mic. Hopefully I won't walk off with it. Today I'd like to discuss nuclear futures for a low-carbon world with wind and solar, nuclear cogeneration with heat storage to buy and sell electricity and assured peak power. Takeaway messages. There are 3 of them. Restrictions on carbon emissions and the addition of wind and solar changes the electricity market, in particular 3 ways: highly volatile electricity prices, 0 and negative electricity prices at some times, and the need for assured electrical generating capacity, no matter what the weather conditions are outside, no wind, no solar, other constraints. A second observation, or takeaway message, is the really big challenge is heat for industry. The electricity sector is the easy problem, so important to keep perspective. In the United States and in Japan, the heat input to industry is about twice the total electricity output. Nuclear reactors produce low-cost heat. Wind and solar produce electricity that can be converted to heat. But if you start with an expensive energy product, electricity, you end up with an expensive heat situation. For that reason, I'm going to discuss a low-cost system design solution, nuclear cogeneration with large-scale heat storage and assured electricity generating capacity. I'm not talking about any specific reactor. I'm talking about the system design, which is distinct and separate, as we will be discussing. I'm going to start, of course, and actually spend about 1/3 of the time describing what are the low-carbon challenges. And I'm going to look at it from 3 perspectives. What are the wholesale electricity markets are telling us today, recognizing they're in transition? What is the optimum system to minimize cost of electricity in a low-carbon world? That's a modeling exercise, but of course all models depend upon assumptions. And last, what is the main non-electrical low-carbon challenge? So let's take a look at the nature of the problem. What are the wholesale markets telling us today? I'm going to use the California case. In the California case here, we show the price of electricity in dollars per megawatt hour on the wholesale market over a 24-hour period of time in the spring in California. The red line shows the wholesale price in 2012 when the system was primarily based on fossil fuels. And the price was determined by the cost of natural gas and coal, essentially. There was a peak in the evening because of peak electricity demand. Now, over a period of 5 years, California added a massive amount of PV. What was the implication on a spring day with low electricity demand? That's the blue curve. Peak in electricity prices early morning, collapsing the price to negative or 0 for about 6 to 8 hours in the day, and then a peak after sunset. And what happened is they added enough solar to drive the electricity price to zero when the sun was out and shining. Now, there are a bunch of constraints on this. There were some subsidies, so they actually went negative. That'll eventually go to 0 when the subsidies disappear. But it tells you what the radical changes are in the electricity grid. But this is a daily example. We need to take a look at the seasonal example. And the example I've used here is California. This is the percentage of time in each month that they have negative electricity prices. That's about a 20% right there. And here we see the monthly up and down of negative prices. And as you can see, there's a very large seasonal effect, as we don't expect. March turns out to be the time of most negative prices. That's a combination of high wind and reasonable solar. July, because of air conditioning load, there's very little negative priced electricity. Now, this has longer-term implications. And I'm going to use some data from the real world, which shows that electricity price collapse limits economic dispatchable wind and solar. This shows the share of all electricity produced in 5 countries by photovoltaic: Italy, Greece, Germany, Japan, and Spain. Each of these countries initiated a very large PV solar program. And the result was a rapid takeoff in electricity production, and then it flattened out. And it never got above 8% in Europe. What happened? By the time they got to 8% in Europe, the electricity, the PV, was providing so much electricity that in effect it collapsed the market, and if you built a new PV system and put it online, there was no place to sell the electricity. It saturated the market, complete saturation. Now, we do not have the wind data yet. We're going to have to wait probably 2 to 3 years before we get real experimental data. I like experimental data, probably in the Great Plains of the United States and in Germany, but it looks like wind is going to play the same game at about 20–25%. What I should also note, by the way, is all the models predicted the saturation effect would occur at a much higher level than it actually did. So much for our modeling capability. Let's look at the models, however. What is the optimum system to minimize the cost of electricity in a low-carbon world? Short, what do the models tell us? At MIT, we've been developing the GenX model to determine optimum electricity generation. It minimizes the cost of electricity with greenfield assumptions. Important caveat. The inputs, hourly electrical demand and weather patterns, capital, operating maintenance costs, fuel costs of power plants, nuclear, wind, solar, fossil, with and without, carbon capture, backup, and storage options. Simulations were done for 6 parts of the world: Texas, New England, France, United Kingdom, and 2 areas in China. And of course, each of these areas has different quality solar, different quality wind, and different cost structures. We looked at it for different carbon constraints from 500 to 1 gram of carbon dioxide per kilowatt hour. Today, the average CO2 emissions of a typical electrical grid are about 500 grams per kilowatt hour. Well, let's take a look at Texas. Now, before we look at Texas, a couple of things you need to understand about Texas. It's got low-priced natural gas. Nobody's got cheaper gas than Texas. It's got great wind and great solar. And it has expensive nuclear. So this is the place to be if renewables is your game, wind and solar. What we did here is we estimated the cost of electricity, average cost of electricity, as a function of carbon dioxide emission limits from 500 to 1 for 3 cases. The blue case, scenarios that excluded nuclear. The orange case, nuclear at a nominal cost, and the gray case, low-cost nuclear. Now, at high CO2 emissions, it turns out you don't build any nuclear. What you do is you build natural gas, natural gas, natural gas, and a little bit of wind. Because if there's not a carbon dioxide emission limit, nobody beats gas in Texas. When you begin to constrain the carbon dioxide emissions, you begin to see some changes. You begin to see a little more wind to reduce the use of natural gas. And when you go to very low emissions, you find out the low carbon option without nuclear becomes much more expensive. And what's happening here is the cost of batteries and other components to deal with the intermittency of wind and solar, and nuclear becomes by far the cheap option. Let us look at the opposite extreme, China. Now, China, this is the Beijing area, expensive natural gas. It's LNG imported from the United States, Texas in particular, and a few other places. Unfavorable wind and solar, unfavorable relative to Texas, not necessarily unfavorable in an absolute sense, but relative to Texas, it's pretty bad. Texas is a really special place, in addition to cheap gas. And they have lower cost nuclear. And in the Chinese case, you find out that nuclear, which is the orange and the gray, depending upon your cost scenarios, is the low-cost option for any carbon dioxide emission limit, including no emission limits. In other words, the Chinese are building a lot of nuclear today because it's the cheap option. And whether you have a carbon constraint or not is irrelevant. Now, let's go a little further into what happened in Texas and what drove up the prices. This is the Texas no nuclear generating capacity increases carbon emissions. This is the installed capacities without nuclear. This is the installed capacities with nuclear. And what you see is happening, if you don't have nuclear in the system, you end up buying a lot of batteries. You end up oversizing the amount of PV. You end up oversizing the amount of wind. And that additional capacity is what's driving up the electricity price. Whereas with nuclear, if you have nuclear in the mix, and it's a mixture of wind, solar, and nuclear, nuclear provides the dispatchable electricity and minimizes the overbuilding of PV, wind, and solar. Now, if you take a look at these low carbon scenarios, what you find out is nuclear energy provides dispatchable electricity, what the system needs. This is the number of ramps per year, the average ramp, and the maximum ramp. And at 10 grams per kilowatt hour, you'll find out that the nuclear plants are changing their power levels 800 times a year. And that's because they're trying to balance the electrical demand between what is being generated by wind and solar and what the demand for electricity is. And nuclear becomes the up and down power source to do that match. When you get down to very low carbon emissions, you're talking about the nuclear plant changing its operations 1,600 times a year, doing load following, replacing the function of a gas turbine in today's electrical grid. Last challenge is, what is the non-nuclear heat challenge? The other half of the challenge, and that one's very obvious, it's industrial heat. Industrial heat input to industry is twice the electrical output. This is the Livermore sources of energy and where it goes. Here's the electric system and total net electricity production. Down here is the industrial sector, and what you find out is the heat input into the industrial sector is approximately twice the output of electrical output of the United States grid. There's a lot of people who say we're going to solve the problem by electrifying industry. When somebody tells you that, they just said they were going to triple the size of the electrical grid. Triple the transmission, triple the generation. People don't understand until they look at these charts what the implications are. Electrification is really very tough on the electrical sector, the industrial sector. That implies that affordable industrial decarbonization may require nuclear cogeneration, heat in industry, heat and electricity. And the reason why is nuclear energy produces low-cost heat. It's a heat generator. That heat is converted to electricity. The heat to electricity efficiency is about 33%. And what that means is the cost of heat is less than a third of the cost of electricity from a nuclear power plant. And that's because it's producing heat. If you had a fusion machine and develop that, it would have the same kinds of economics. Concentrated solar power, geothermal. If you produce heat and you need heat, that's the cheap way to do business. Wind and PV produce electricity. Unfortunately, you can convert electricity to heat, but it's very expensive. You're starting with an expensive product to create a low-quality, low-cost form of energy. It's just an intrinsic nature of thermodynamics that's working against you. You also have this problem of require storage for hourly to seasonal steady state. So that's the nature of the problem. And what we're looking at is rethinking nuclear energy system design for a low-carbon world. It's not reactor specific. And it's to match the reactor system capabilities to minimize total costs, because cost is what ultimately will drive the choice of decisions. Now, if we take a look at what we've said, what do we need? What does a low-carbon energy system need for a real world? We need to first sell dispatchable electricity. That's the problem, replacing the gas turbine. That is the challenge. We want assured generating capacity for peak loads, whether the sun is shining or whether there's any wind. We want the cost to be reasonable, and we want to be able to do this on an hourly to seasonal basis. Second observation, we want to buy and consume very low-priced electricity from wind and solar at times of excess production. Negative-priced electricity is really bad for solar. Negative-priced electricity is bad for wind. And negative-priced electricity is bad for nuclear. It's just plain bad. You can't run an electrical system if there's no revenue. It's just one of those realities. You can use taxpayer revenue, but that gets to be a very expensive option. So we need to buy electricity if the price gets too low. And last, we need to provide process heat to industry. This leads us to a new nuclear system design. We have here the baseload reactor. The reactor operates at steady state. It could be any type of reactor. This is not specific to nuclear technology, the specific nuclear technology. Produces steam. The steam can go in two directions. First, it can go to the turbine hall where heat is converted to electricity to produce dispatchable electricity to the grid. If there is a low demand for electricity, heat from the reactor is sent to a heat storage system where we store that heat, where we heat up some material, hot salt, hot rock, hot sand, hot concrete. There's a list of about 20 of these, and we store heat in this system. If we need a lot of electricity, we have the full power of the reactor going to the turbine hall, producing steam, and steam from heat storage going to the turbine hall to produce more electricity. So we produce peak electricity in a dispatchable form. Now we have on the system wind and solar. When they're available, that's fine, but they may crash the price of electricity, and we have excess electricity. If we have excess electricity on the market, that means zero priced electricity, or electricity less than $10 a megawatt hour. We buy the electricity, and we convert that excess, very low priced electricity into stored heat that can be used to produce peak power at other times. So we buy and sell depending upon what the electricity grid needs. Now, the central problem with storage, of course, is it can become depleted. It doesn't matter what kind of storage device you have. So we add a steam boiler at times when the storage is depleted that can also produce steam to replace the heat from storage and guaranteed peak power production. Now, the feature of these types of boilers is the capital cost is about a third of the capital cost of a gas turbine. They're really, really cheap. The other feature is if you have very large storage, this machine may only be used 100 or 200 hours a year. It's there for when you have a bad day. It's a low performance boiler. And the reason why is if you have 6 or 8 hours of storage here, you know when you're going to run out of storage, so you can tell the guy who's running the steam generator here, please start up the boiler, and we'd like it in about 3 hours. So it's not a high performance, expensive furnace, because you know a long time in advance before you're going to run out of heat storage. So the thing about this is it's assured capacity at low cost, absolute requirement. The same system, of course, can produce industrial heat. Let's take a look at the components of this. First, there are lots of heat storage technologies being developed that couple to nuclear. Not surprisingly, they're the same ones that couple to concentrated solar power plants. Some concentrated solar power plants now have heat storage at the gigawatt hour scale. I mention that because, you know, the battery people think they've really done something when they're at a megawatt hour. Concentrated solar and nuclear people look at a megawatt hour, they say, well, that's obviously a laboratory experiment. You're going to be serious, you've got to be in the gigawatt hour, or gigawatt month, or gigawatt year scale. Not small scale. Several technologies are deployed. Steam accumulators are deployed at a number of solar power plants. Sensible heat storage is at some other facilities. This is where you heat up hot oil, hot salt, which is done commercially today, but there's a whole bunch of other processes under development that I'll briefly describe. There's something called cryogenic air, which is a talk all unto itself, so I won't cover it. People are working on hot concrete or hot cement. These would be the steam coils buried in a cement monolith, and they're designing those to go up to 600 Celsius. So this is not your normal Portland cement that they use to do the road. People are working on hot rock, and they're working on geothermal heat storage, where you heat up a chunk of rock 300 meters by 300 meters, 2 kilometers underground for seasonal storage. In all of these cases, you dump the heat in, you take the heat out when you need it. Second observation, if heat storage, buy low-priced electricity and convert to heat for later use. And this is the issue of very low-priced electricity. So you buy low-priced electricity, use resistance heaters, and convert the heat into the electricity into heat. Now, what is very important here is this is a really low-cost storage option. And the reason why, if you think about it, well, let's see. I'm a power plant. I'm selling electricity to the grid. I own transformers, grid connections, switchgear. That same equipment that's used to sell electricity can be used to buy electricity. No additional capital cost. I've already bought my heat storage system for other purposes, So all I have to do is make this heat storage system incrementally larger. And so with one of this type of system design where you have heat storage coupled to a heat generator, you have the ability to buy electricity when it's cheap at very, very, very low cost. And this is currently being considered by a number of solar systems in the Southwest United States. I have not heard yet a decision to actually implement it. There's some regulatory rules that have to be addressed. But my guess is that people with heat storage are going to gobble up cheap electricity if somebody wants to sell it at under $10 a megawatt hour. Second observation, this kind of system can address the weekday, weekend market challenges. Low carbon systems have excess low price electricity on weekends because of low demand. 5-day work week, weekend much lower electricity consumption, lots of excess energy. And what that means is on the weekend, you can buy that excess electricity and dump it into storage. And of course, the reason that works is the incremental cost of heat storage is very low. And this is what we're talking about, the incremental heat storage costs, whether you're talking about pressurized water, geothermal, cryogenic air, hot concrete, hot rock, hot sand, hot oil, hot steel, hot nitrate salt, or hot chloride salt. That's the list that there are currently significant programs in, by the way. It's not clear which heat storage technology will win. Probably multiple ones will win because of different temperatures, but a lot of people are working on the problem either for nuclear reactors or for solar. However, it's the same technology, so a number of companies, the answer is we'll sell to whatever customer is available. The last observation is if you have heat storage, the option to buy a steam generator or furnace for assured power. Again, all storage devices can become depleted. You need assured peak power. That's what the real crunch problem is in a low-carbon society. You already bought the turbine generator for peak power, and what you're doing is it's a low-cost option because you're buying the steam generator to replace heat from storage when storage is depleted. And again, the cost of these things is a half to a third of that of a gas turbine. You know, this is all about driving the cost down. It's all about economics. Brief look at nuclear cogeneration, which is the other half of the problem. We did a Gen X model of what happens if you tried to electrify industry, run electric wires to it, and see what the price impact is. And the case we used, of course, was Texas. And we used the case of where you have an electricity option where you tried to electrify industry. And what we found is electricity prices went down with added baseload electrical demand or heat demand because of the better match between production and demand. What we have here is 4 curves. This is the no nuclear nominal electric demand in the orange. This is the no nuclear nominal industrial heat demand. This is the nuclear nominal electricity demand and nuclear with the additional heat electric demand from industry. In the case of no carbon constraints, natural gas, natural gas, natural gas, and a trace of wind. The reason why the cost went down, however, was the change in the optimum generating mix. You went from a mix of gas turbines, combined cycle gas turbines with efficiencies of about 62%, coupled with single cycle gas turbines with an efficiency of about 40%, because you have to meet the variable electrical demands, so you don't build one type of technology. If you add a lot of baseload technology, you better match the electrical demand with the production technology. And what you find out in these cases, if you have this industrial load, is you end up buying all combined cycle gas turbines. And of course, natural gas is cheap, and a combined cycle natural gas turbine is the most efficient machine on the planet Earth to convert natural gas into electricity. So if you couple production with electrical demand, so you have efficient use of resources, the costs go down dramatically. So natural gas wins in Texas if the carbon emissions are low, if there are no carbon constraints. If there are serious carbon constraints, nuclear wins, and it's the same situation. What happens in this case is the nuclear plants operate essentially at base load or very close to base load, and they're producing most of that energy that goes to the industrial sector. And so you have an efficient coupling, an efficient use of technology between nuclear and and the industrial suppliers. You do get, of course, more wind and solar here, and this depends very much upon what the actual price of PV and wind is. And it varies depending upon where your location is. So you'll get a fair amount of wind and solar if you're in Texas. You aren't going to get very much if you're in New England, which has lower, poorer conditions. Now, the same system applies to nuclear cogeneration. I got a heat production machine, a heat storage machine, assured capacity. So the industrial demand goes here, and you couple the nuclear sector, or the electrical sector, with the industrial sector. And what that really says is that you're optimizing the costs over most of the energy demand of the US, not just optimizing over the electricity demand. And however you do that, if you can couple these two the industrial sector with the electric sector efficiently, it will drive down the cost. It doesn't matter what kind of technology you have, because it allows a better optimization. You have more variables to change. That makes a tremendous difference in the cost structure of these systems. Now, some characteristics of nuclear cogen with heat storage. Again, integrate the electrical and industrial sector. Second, which is not appreciated, some existing fossil cogen plants vary industrial production for more electricity production, higher electricity demands, and less production when low electricity demands. The same option for nuclear cogeneration. Many of you are probably not aware of it, but there are many gigawatts of what they call cogen plants. These are electrical plants, fossil plants that produce heat and steam and electricity. They need, of course, the steam for the industrial process. They sell the electricity to the grid, but they can vary how much electricity versus how much heat to the industrial demand. And depending upon the price of the industrial product and the price of the electricity market, they can vary production of the product versus electricity. And it results in a significant savings to the overall system. So cogen's a really efficient way of coupling the two systems together to minimize costs. Last, for the nuclear plants, much lower financial risk with nuclear cogen versus nuclear plants just for industrial heat. Nuclear plants have long lifetimes. Changes in the industrial processes may change the industrial heat demand over a period of a decade or 2 decades. So there's a lot of incentive from a financial point of view if you're in the cogen market. But much more important than that cogen market is this ability to optimize a big chunk of the total energy demand of the world, not just the electrical sector, which is one small, it's important, but it's only one segment of the sector without it having it being decoupled from the industrial sector. So you need to think about the whole problem. I'd like to emphasize it's you can't stovepipe. Stovepiping gets you expensive solutions. You have to consider the entire system. Well, some conclusions. The most important one is the electricity market is changing. Cannot be overemphasized. Wind and solar are cheap, but they're non-dispatchable, and that changes the market. The goal of a low-carbon economy changes the market, and those changes imply dramatic changes in the next decade, 2 decades, relative to the last 300,000 years. I don't know if you've ever thought about it, but we haven't had an energy policy change in 300,000 years. Whether you're talking about the cooking fire of the caveman or the modern gas turbine, all of the money, or most of the money in both of those systems was collecting the fuel and bringing it to the fire. We've been operating that way for 300,000 years. We're now in a situation where we're trying to kick out the fire, and we're buying capital-intensive technologies, wind, nuclear, and solar, and to make them work, we have to use them at high capacity factors. But the market is changing, and we're going to have to adjust the technologies to match it. Low carbon requires a replacement for fossil fuels, the energy source, storable energy, and dispatchable energy. You know, coal and natural gas are amazing products. Replacing these products is going to take a great deal of effort. Last, we require a new system design, nuclear cogeneration, heat storage, and assured generating capacity. We want to integrate the electricity in industrial markets to minimize cost. It's all about minimizing cost. It also, interestingly enough, enables economic large-scale use of wind and solar PV by solving the storage problem and the assured generating capacity. If you want an economic system, you've got to have something that guarantees the power is there when you need it. but can also buy very large quantities of electricity when the price is too low. Well, with that, I will open the room to any questions you might have. And of course, I'm also in MIT, so if you're looking for me or want a copy of these slides, just send me an email. Thank you very much.
So much. Just to remind everyone to state your name and affiliation as you start. Thanks for the great talk. A really important view on systems. So I think there is a question here in the front.
Yeah, I'm Todd from Arizona State University. Two questions. One is the ramp-up time. When you say nuclear, solar, wind cogeneration, okay, thank you, sir. Yeah, what do you call it? The valuation is on the order of minutes to hours for wind and
That's right.
So can nuclear ramp up and down that quickly?
You can. That's not the issue. The question is what is economic to do.
Okay.
And the game is to run the nuclear plant steady state and let the turbine hall and the heat storage system do all the ramping. And that's much cheaper. That's, the whole game is for the nuclear reactor operators to be totally bored, quiet, dull. The turbine hall and the heat storage people operating that, things are just lively as can be. More power, less power, buy electricity, sell electricity. So we want exciting turbine halls and dull reactors.
Another question, second question. Another question is that I think the problem, last year I spent a year in Sweden as a Fulbright chair, and so one thing I noticed is that in most European cities you have this centralized heating system.
Yes.
Yeah, but here when you see nuclear and heat cogeneration, but you have to transport the heat long distance to industrial centers where the heat is needed. So that could be another problem.
Well, for large industrial complexes, there are reactors that have been specifically designed to be next to a large industrial complex with the right different kind of safety features. There's what they call high temperature gas cooled reactors. Heat you can actually transport 10 or 20 miles. In fact, you can do actually 30 miles, and that's mostly thanks to our friends in Iceland, who over the last 50 years have been really big into geothermal. And Reykjavik is here, and the geothermal's over there, and they have gotten really, really good at developing the technology for extraordinarily low heat losses. If somebody had told me 20 years ago that they have a couple of % heat losses, I'd say that's crazy over that distance. But they've learned how to do it because they had a need, and that technology is now available to move hot water very, very long distances. But that's only in the last 10, 15 years, thanks to our Icelandic colleagues.
Question right here.
Hi, I'm Robert from Harvard. So I had a question. So you mentioned trying to provide heat for industrial processes,
Yes.
and we already do that. But what about moving to more electrochemistry in industrial processes? I'm thinking making steel is a big heat source or heat sink.
If you're making steel, you're going to be making hydrogen to make steel, because the first requirement of steel is a chemical reducing agent to replace coal as a chemical reducing agent. And that'll either be electrolysis or high temperature electrolysis, which is more efficient, which is steam plus electricity. But this is an industry by industry by industry game. There are no generalizations that you can make.
I didn't say it would be easy. Have you looked into that?
People have looked into that, but the issue is going to be cost. The Swedes are starting a pilot plant with low carbon steel production, as you're probably well aware of. And they're saying maybe on a good day it'll only cost 25% more than current steel. If you have commodities that go up by 25 or 50%, this is not good news for society. By the way, for something like a steel mill and a cement mill, the debate will be between hydrogen and natural gas with running the industrial processes with natural gas and sequestration. So those are the competition. In Texas, my suspicion is natural gas with sequestration is going to win. Not nuclear, not wind, not solar, natural gas with sequestration, because they have such cheap natural gas.
Hi, Ian from University of Lisbon. So Your very last comment kind of has an impact on this. But so you're saying these nuclear investments are basically economic, so we should expect them to kind of
Yes.
show up in the private sector. We don't need any government support, no
Well,
public money.
the government is involved in any case, but if you go to an all renewables economy, you will run the costs of we did something called the future of nuclear power in a carbon constrained world. And what you find out is the all renewable schemes become unaffordable as you go down in CO2 emissions. And it's the problem of storage, and more storage, because there's no cheap way to store electricity on a daily to seasonal basis.
So to a degree, this is just what we expect to see happen. There's not a specific change that we should make.
Oh,
now
well,
to-
no, you should do a lot of things if you want to do this in a short time frame. And the question is, what's the time frame? If you'd like to do something in 20 years, you need a lot of demonstration projects and other projects, because the whole issue here is time. If you're waiting a century out, there's no question. But if you happen to want something like in 20 years, then you're going to have to push a lot of technologies very hard.
We have time for another. I think we can probably do both. I'm not sure who was first. Here we go.
So my name is Xiao Yuan from MIT. So we know that for heat storage, heat has a quality, for example, low temperature and
That's
high
right.
temperature heat. So what is the proportion of this heat in the heat storage system that you are talking and to incorporate with industry heat?
Say that again?
So what are the proportions, for example, the heat storage systems, are you storing high temperature, low temperature,
The temperature depends upon what type of reactor you have. The system size of each component will depend upon the specific market you're in. The market in Arizona with solar will be very different than the market on the Great Plains with wind. Not a single solution. Depends specifically upon the market you're in.
And I think we have time for one more question, but it has to be brief so that we can keep on track. Thank you.
Jos Haverkort, Eindhoven University. Can you comment on the efficiency of access electricity to heat and say heat back to electricity? What type of efficiency?
Depends whether, well, in LWR it's going to be around 30%. With a high temperature reactor it's going to be around 50. And with some advanced power cycles you're up in the 60s. But this is not a question of thermodynamics. This is a question of economics. And it all comes down, what is the minimum cost system? It takes a while for those of us with an engineering training to get the challenge of cost. But this is all economics.
Clearly, we could keep talking about this all day, and we will. But thank you so much to our speaker, and we'll move on for the